Hello and welcome to Engineering Economy. This is Dr. Ola Kamerdiner. We will talk today about inflation and price change. The topics that we will discuss are meaning and effect of inflation. We will also talk about analysis in constant dollars and compare it to analysis in actual dollars. And we will talk about price change indices. We will also talk about cash flows with different inflation rates, and we will talk about effect of inflation on after-tax analysis. Last but not least, we will discuss spreadsheet and inflation calculation. So the learning objectives for today is to be able to recognize the impact of inflation in economic analysis. And we will also define real and actual dollars and interest rates. We will be able to conduct real and actual dollar analysis, and we will be able to understand and apply price indices. We will develop cash flows with different inflation rates, and we will be able to incorporate inflation in both before and after tax calculations. We will use spreadsheet to incorporate the effect of inflation and price change. So here's a quick story. The Athabasca oil sand. The Suncor, when it was formed in 1967, was known as Great Canadian Oil Sand Company. And in 1967, the target production was 31,000 barrels per day, and the initial cost was about $25 a barrel. The oil price was $3.50 a barrel. The production cost has been reduced to about $12 a barrel in 2004. However, production cost has been increased rapidly since 2005 and approached $28 a barrel in 2007. Suncor is targeting average oil sands production of 255,000 to 265,000 barrels per day in 2007 with 5,500 employees as of July 2007. World price of oil is about 70 in 2007. So here are some questions. The oil sands projects would have 10% rate of return when the world oil price reached 25 per barrel. How will inflation affect these estimates? How do we know if inflation is occurring? How could we measure it? The Canadian Consumer Price Index, or CPI, was 21.5 in 1967, and it is 123.2 in 2004. Given the production cost of $12 in 2004, what was the production cost in 1967? Search on the internet to learn more about Athabasca oil sand. Are there any environmental and/or ethical dimensions to the story? So let's start discussing the meaning and effect of inflation. Inflation causes money to lose purchasing power, and inflation makes future dollars less valuable than present dollars. In other words, what we were able to buy 10 years ago, now we would need to pay more money to buy the same items. And deflation can also occur, and deflation occurs when the purchasing power of a monetary unit increases. And in many countries, the inflation is so high that it becomes a hyperinflation, and that's when something that maybe used to cost $10 then becomes $100 very rapidly, and then in other months it becomes 1,000, and so on. And deflation can also happen during, in order to combat hyperinflation, the currency might be discounted and exchanged to a lower denominations, and that could change and deflate the amount of money. However, there are other things that could also cause it as well. And so inflation and deflation are basically the two sides of the same coin, and that's a difference in terms of purchasing power of money. So the money in 1 year is not necessarily the same in terms of its purchasing power as the same amount of money, right, the actual cash, but the next year or in some of the previous years. So how does inflation happen? Well, there's different theories regarding that, and one of it is money supply. Money available to the consumers in general economy increases faster than the goods available, and it creates inflation. There is also an exchange rate argument, where price change reflecting comparative value of currencies in different countries. And there is also cost push, in terms of producers raise prices to cover cost, or demand pull, consumers bid up prices by attempting to buy more than is available. So let's talk about some interest rate definitions that are connected to inflation. So first we're going to talk about inflation rate, and we denote it F, and that's the annual rate of increase in dollar amounts needed to pay for the same amount of goods or services. There's also two different rates, the real rate and the market rate. So far we've been using market interest rate, and we denoted it by I. And that's the interest that one obtains in a general marketplace, also known as a combined interest rate. So far we talked about the market rate, and that's an interest that you might have when you store your money in a bank, or if you invest in the stock market or in some other opportunities. So this is your interest rate. There is also this real interest rate, which is a little bit confusing of a name, because even though it says real, it's quite an abstract concept, because that's an interest rate of the real growth of our money without the effect of inflation. And that's also known as inflation-free interest rate, and we denote it by I prime. So I prime is this real interest rate that actually takes the effect of inflation out of the equation. And speaking of equation, this is an equation that connects the market rate with the real rate or inflation-free rate and the inflation rate. So 1 plus I is actually a product, could be decomposed as a product of 1 plus the real rate and 1 plus the inflation rate. So from there we could simplify. If we multiply these, we can simplify and get rid of the ones, because 1 and multiplied by 1 is 1, and this one they can cancel off, and so this top equation simplifies to this bottom equation here, where the market rate is then the sum of the real rate or inflation-free rate plus the inflation rate plus the product of those. And so here let's take a look at an example where we have a bank that pays 5.5% interest compounded annually. Inflation is expected at 2%. We want to identify the market rate, the inflation rate, and the real rate or inflation-free rate. So what is 5.5? Well, it's easy to understand what it is, right? It says bank pays. So that's actually your marketplace. The marketplace allows you to gain this interest rate. So 5.5% is the market rate I. And it's different from the I prime, which is inflation-free rate. So what about the inflation rate F? Inflation rate F is 2%. So now we have the I and we have the F, and we can determine the I prime based on the first equation that we had there, the top equation. So now this is our I and F. We're plugging those values in. So we plug in 5.5 here. We plug in the 2% here. So then we just divide those, right? And so this part right, by dividing both sides by 1 plus f, which is non-zero, so we can divide by it. We get 1 plus I prime, which is 1 plus the real rate that we want to find. It's just a ratio of 1 plus I divided by 1 plus f. And so then, right, we just gonna subtract the 1 from this, from both sides. So that will give us the I prime. So evaluating all this, we're gonna get 3.4%, and that's the inflation-free rate. Here's another example. Bank pays 5.5% interest compounded annually. Oh, that looks again, right? Bank pays, right? That's our marketplace. So that again looks like the market interest rate. So 5.5 is I, and then it says inflation is expected 8%. So now we just have a different, it's very similar as before. The only difference is now the inflation is not 2%, but instead it's 8%. Notice that it's larger than our market rate. So can we find the I prime? Of course. So again, the same exact way as before. We set up the equation, and from which we can find this is actually 2.3%, but negative 2.3%. And that's not surprising, right? Because you can see that here this on top is less than what we have on the bottom. So this is less than 1, and then we're subtracting the 1, so it's gonna give us a negative value. So what actually it says is that in this case this real rate, right? Remember, the real rate is an inflation-free rate, and the real rate is negative, so we're actually losing the money. Well, here we were gaining the money, right, after discounting the inflation. The real rate of the growth of our money was 3.4, the positive rate growth. So we were gaining some money, where here we're losing some money after taking into account the inflation or discounting for inflation. So now let's talk about the concept of actual dollars versus real dollars. So we need to introduce a few definitions. So actual dollars are actual dollars that we can hold, right? It's either in the bank, or you can have some money on your card or your cash in the pocket. That's actual dollars, right? That's in circulation. And they also called inflated dollars because, right, from year to year their purchasing power changes. Then there's this abstract idea of real dollars, just like the real rate was an abstract idea that was inflation-free. The real dollars is an abstract idea that also denotes a inflation-free dollars, right? So it's an abstract idea. It's not something that you can actually physically have. So dollars was a constant purchasing power and always expressed in terms of base year, right? So it depends on what year we're gonna, right? We take 1 year, we say this is gonna be our base year. We're gonna look at everything in terms of purchasing power for, of the dollars that we had during that year. And so again, these real dollars are inflation-free dollars. So we're gonna use the market interest rate I with the actual dollars, and we're gonna use the real interest rate I prime when dealing with the real dollars, right? So we're using inflation-free rate I prime when using with inflation-free dollars, and here, right, the real dollars are denoted by R and then the dollar sign, and the actual dollars are A and the dollar sign. Alright, so now if you look at this, let's say we start at some time point T. The time point T is going to be our base year, and then some time going to pass, exactly n period is going to pass, and then we have some time n. So there is actual dollars at time T, and there are some actual dollars at time M, and we convert between those as we always did, right? As we did so far, we just use this market rate. So what we did before is we used this market rate to convert from one actual dollar to another. We didn't really talk about the dollars being actual dollars, but now we know that those were actual dollars, and that was the inflated dollars, and this was the market rate, or the rate that included inflation. But now, right, we can also convert each of those actual amounts into the real dollars. And so we would have the real dollars in terms of base year t at time t, and then the real dollars in terms of base year t at time n. And so we convert between these two using the inflation-free rate or the real rate, I prime. Of course, notice that the actual amount at time t is the exact same amount as the real dollars base t at time t. These two are the same. This value is the same as this value. Why? Because there is really no inflation happening between these 2 years, right? This is just the 1 year, right? T and T is just a single year. So there's not really 2 years, there's only a single year, so there's no inflation. But here, this base in time n, right, you need to discount this inflation-free dollars would not have the inflation that we have here. So these two do not equal to each other, because this actually we need to discount the inflation that happened during n years. So here we had f, or inflation rate, f, for 0 periods, right? Because between t and t is just 0 periods. But here we have n periods, so we have f, rate f, for n minus t periods. So to make this a little more clear, let's take a look at the example. And here we have a real interest rate calculation. A stadium was built in 1955 at 1.2 million. At the same year, a gift of the same amount was invested at the market rate of 8% per year. The inflation was 6% from 1955 to 2010. We want to define the market rate, the inflation rate, and the inflation-free or real rate, I prime. So that's simple, right? We can see market rate, says market rate, 8%, that's I. And then inflation was 6%, so that's F. And then we can find I prime, just like we did before. So then we also want to know how much actual dollars the gift will be worth in 2010. Well, in terms of actual dollars, what we need to do is we need to take this 1.2, that was in 1955, that's a gift of 1.2. And then it's gonna grow, right, and become some future amount in 2010. It will grow at what rate? This is the actual dollars, so it will grow at the market rate, because we're using market rate with actual dollars. So we're gonna use I here. So here, this is the future amount, this is the past amount, FP. So we multiply by FP, and then I, because we use with actual dollars, we use I, market rate, and then between 55 and 2010 there's 55 years, so that's what we have here. Then we just evaluate this, right, plugging in I being 8%, and that gives us over $82 million. So here's another question for the same problem. How much the gift will be worth in 2010 in terms of 1955 purchasing power? So notice now it doesn't say how much it will be worth in 2010. It also says or adds this in terms of 1955 purchasing power. So what we really want to see here, right, because it says about 1955 purchasing power, it actually tells us about what about the base year, how much does it really worth, right? So it really means real dollars. So here we want to see real dollars. So R base 55 at 2010, and that's based on R base 55 at 1955. So R base 55 at 1955 is the same as A at 1955, right? Because there is no inflation, there is inflation during 0 periods. So we just have 1.2 million. And then, right, this was the future, 2010. This is the past, so F given P. And these are real dollars, so we're using real rate or inflation-free rate I prime. And again, between 2010 and 1955, you have 55 years. So then plugging in the value of I prime that we found earlier, plugging in here, and then evaluating this F given P, multiplying it by 1.2 million, we'll get 3,357,000. So notice that is quite different from that 82 million we had before, right? See? We had over 82 million. So that was the actual inflated dollars, but in reality, that's how much you can really buy with those 82 million dollars. In terms of course, 1955 purchasing power. Alternatively, we could have done it in a different way, right? So we could have taken, we already found actual dollars in 2010, we could just take those actual dollars and discount the effect of inflation. And discounting is just basically dividing by 1 plus F to the number of periods. And we had 55 periods between T, this is T, and this is N. So N minus T is 2010 minus 1955, 55. And so this is just an alternative way, which gives us the same result as this. So now, if the gift will be used to build a new stadium in 2010, how much better or worse the new stadium is gonna be? So what we really want to do is we want to divide, right, the actual amount by how much it was in 1955, right? So this is in terms of 1955. We want to divide, right, by how much the gift was, right? So now we're dividing the R base 1955 2010 versus how much it was in 1955. And so this is what we do, right? We divide it. This is going to be 2.8. So it's actually, the stadium is going to be 2.8 times better. Alright, here's another example. 1,000 worth of quarters were buried in the backyard in 1924. Average inflation was 4.5% from 24 to 94. What was the relative purchasing power of these quarters? Again, right, what do we have? We have $1,000 worth of quarters. They were buried in the backyard, so they weren't getting any interest. So the market rate on these quarters was basically a 0. But there was some inflation of 4.5. So we want to find the relative purchasing power of these quarters in 94. So what we're really looking for, right, is again the relative purchasing power. So it's going to be the real dollars amount at 94, with the base year being 1924. And that's what we have. So again, what we can do is we can take the actual amount in 94, which those 1,000 worth of quarters, they still remain to be 1,000 worth of quarters. They didn't gain any market rate because market rate was 0 when you bury something in the backyard. So then you have the actual dollars we can discount in 94. We can discount them based on the effect of inflation. From 24 to 94, there was 70 years or 70 periods. So we divide by 1 plus the F, which is the inflation rate, to the 70, right, which is the difference between 94 and 24. And so then plugging in the values, right, we plug in 4.5 here, the inflation rate. And so then plugging in the values, we get just $45.9. So it's a little less than $46, right, versus it used to be $1,000. Now you can only buy 45.9 worth with those quarters of what you could have bought in 1924. So if 1,000 was instead invested in the stock market in 1924, how much it will be worth in 94, given that the stock market increased an average of 15%? Well, here, in order to be able to compute that, we looking in terms of first finding the value, actual cash value in 94 of the money invested in 1924. So we had the 1,000 in 1924, that was the past. This is going to be the future, right? Again, we are looking at the actual amounts at first. So actual amount in 94 is going to be actual amount in 1924. So this is the future, this is the past. So FP multiplied by FP, right? So it's the same as before. And then we have I here, which is the market rate, because we're using market rate with actual dollars, right? The actual dollars requires a market rate. So the market rate, right, stock market increased 15%. So that's our 15% is our I. And then the difference between 94 and 24, as I said before, is 70 periods. So 70 years is here. And then plugging in the 15% instead of the market rate I, and plugging in 1,000 for actual amount of dollars in 1924 that we have, we're gonna get this, which evaluates to over 17 million. So then, right, how much it will be worth, right, in terms of 1924. If you wanted to ask that, then we would want to find the real dollars in 94 with the base year being 1924. So real dollars base 24 at 94 is going to be the actual dollars in 94, which we just found, and then we discount the effect of inflation. So divided by 1 plus f to the 70. And so we divide what we just got, right, by the inflation rate, 1 plus 4.5% inflation rate that we know, and then to the 70, so that gives us 814,069. So these money would actually be worth this much, right? So there was appreciation, right? The 1,000 did grow significantly to over 800,000. So that was over 800 increase. So here's another example of where we have the real interest rate calculations. If 1,000 was invested in the government bonds in 1924, how much it will be worth in 94, given that the bonds average 6% return per year? So again, we're still using the inflation rate of 4.5 as we did before. So again, looking at actual dollars in 94 based on actual dollars in 24, and to convert from actual to actual, we're using the market rate I. So now the market rate is 6%, right? Because now we're investing it in bonds, we're obtaining it from the market, so 6% is the market rate. So we're going to plug in the market rate here. This is still futures, this is the past, so FP, and then 70 is the difference between 94 and the 24, so 70 years. Plugging this in evaluates to 59,076, and then we can find the real dollars or the inflation-free dollars. So in 94, in terms of purchasing power at 24, it would be the actual amount that we just found, and then it's going to be discounted for inflation because we want to get the inflation-free. So 1 plus f to the 70, again plugging in the 4.5 here instead of f, and then we get 2,712. So it's about 2.7 times appreciation. So now let's talk about analysis in constant dollars versus then current dollars or the actual dollars. So when we look at the analysis in constant dollars, we're ignoring inflation in analysis. And most costs and benefits have price increase at about the same rate as general inflation. We use real dollars and real interest rate I prime, which is the inflation-free rate and inflation-free dollars, right, or constant dollars. When we perform analysis and then current dollars or actual dollars, we incorporate inflation in the analysis, and we use actual dollars denoted by A dollar and the market interest rate I. So now let's take a look at the example. So here we're comparing two companies, company Alpha in company beta, we have information about our company alpha in actual dollars, but for company beta, we have information in real dollars. So we need to compare apples to apples, right, or actual dollars to actual dollars, or oranges to oranges, which means real dollars to real dollars. So we could, for example, compare real dollars to real dollars. Then whatever we have in actual dollars, we need to translate into a real dollars. So here you can see this 150,000, and then we have next year's this 5% additional return. But we also need to take into account inflation of 3.5. So here we divide by 1 plus 3.5%, and this is the first year, so just to the 1, but in the second year it's going to be to the 2, in the third year to the 3, and so on. So then, right, this gives us the values in terms of real dollars, right? So then we can compare this with this, and if you look at this, you'll get to compare between these dollars, we need to get the inflation-free rate or a real rate. And so we already know the inflation, which is 3.5%, and we know that 5% is the market rate. So plugging those in, we can get the real rate, and then calculate the present worth of cost for alpha versus present worth of cost for beta. And so you can see, right, based on the cost, the alpha has a smaller cost. So here's another way. So exact same situation, company beta still has this. We could translate it into actual dollars, and because for company alpha we have actual dollars. So then again, right, if we have actual versus actual, so it's the same exact example. The only difference is that here it's an alternative solution, where instead we comparing actual dollars. Before we were comparing the real dollars. Now we're comparing the actual dollars, so we cannot no longer use the inflation-free rate. We should be using the market rate, which is I. So the market rate is 25% as before. So then we'll get present worth of cost for alpha, present worth of cost for beta. Again, the alpha has a smaller cost, so we would select the alpha. So now let's talk about price change with indices. So price indices, they actually describe real price fluctuation of goods and services, and price indices are tracked for a specific commodity or for bundles or composites of commodities. We use past price changes to predict future prices, and all price indices have a base year, which is assigned a value of 100. So here's an equation which could be used to find the price index in year T. It's simply price in the year T divided by some price in the base year, and then multiplied by 100%. So now that we know about price indices, we can look in terms of how we can estimate those. So there's different ways to estimate it. So we have annual percentage increase, and that's annual percentage increase in year T. It's just simply difference between indices for T in year T and year T minus 1 divided by index T minus 1, and then multiplied by 100%. And there's also average rate of price increase, which simply, right, which you find this average percentage increase between years, not necessarily consecutive years, T1 and T2. So the second year, the T2 index divided by the index of the first year, T1, and then we take a root of T2 minus T1, and then we subtract 1 from this whole thing, and multiply the result by 100%. So that gives us the average rate of price increase. So here's an example of price change with indices. A new building in Los Angeles cost was 1.3 million in 97. How much will it cost in 2010? So we could find California Construction Cost Index. In 97 it was 3,473, and then this California Construction Cost Index in 2007 was increased to 4,869. So then, right, again, using this, right, and in terms of what, if you wanted to know where to find these construction indices for California, here's the web page. So then we can find the average percentage increase that will give us the simply the inflation rate, right, or change inflation rate in terms of how much more the buildings would cost. So between 97 and 2007, right, these are the years that we have the indexes for. So we take the 2007 index, right, plug in here, and we take the 97 index, plug in here, and then take this ratio and take a root, because here we have from 2007 to 97, we have 10 years between those, then the difference will be 10. So this is what the root in terms of degree of the root that we have, and then minus 1, and then this whole result is multiplied by 100% to get the percentages, so that will give us 3.44%. So simply said, that gives us, from the price index, we can get this inflation rate. So that's increase in terms of the price of the building. So that's between those 2 years, but we need to find one in 2010. So we have this 3.1 million in 97. We can find 2010 using this inflation rate, because from 2010 to 97 we have certain years, right, during which the prices were increasing or purchasing power was decreasing at this inflation rate of 3.4%. Then we need to inflate this amount by certain years, right, of this inflation rate. And that's what we see in terms of actual dollars in 2010. We have actual dollars in 97 multiplied by 1 plus f to the 13th, where f is this estimate here based on the price indices. So we plug in this 3.44% and certain years between 2010 and 97, and then this 1.3 million here that it was is now grew in 2010 grew to 2,016,967. All right, here's another thing that we want to talk about, that we want to discuss regarding consumer price indices. It actually, this CPI or consumer price index inflation rate was changing all the time. So you can see at some years it was higher, at some years it was lower. So you can see how it was changing through the years. And this could be found from this link. So now let's take a look at the example of cash flows that inflate at different rates. So in this case, as you know, right, we could have different commodities, and so the cost indices or price indices, right, are prices of different commodities. In this case, we have electricity separate from the water, separate from the natural gas, and for electricity we have this 8.5% inflation, and then for the water we have 5.5% inflation, and then for natural gas we have 6.5% inflation. So then if we have all those different prices and we can incorporate the inflation there, we're going to get the totals when we add them all together, of course adjusted for inflation. And then we can find the present worth, which, right, for each of the totals we then discount it based on the rate, and then however many periods we have. So that will give us this estimate for the present worth of all of these utilities, right? The electricity, water, natural gas. This is going to be the present worth or the cost of these utilities throughout the years. So here's another example. Not only is the inflation can change based on the different commodities, but there could be different inflation rates per period. And so you can see for lima beans during the years 1 through 3, the inflation was 3%, but then starting year 4 and then year 5 too, it was 4%. For corn, we had during year 1 and 2, we had inflation of 8%. The prices were increasing 8%. But then in the later years from 3 to 4, notice it's actually less than 1. So there was a 2% deflation. So this is example of deflation. So it's 1 minus 2%. So this negative inflation is deflation, as you remember. And so this negative 2% deflation for corn, or decreasing prices for the corn, give us, right, in those later 3 years, the 3, 4, and 5 years, we get smaller prices. And so together, if we buy in both lima beans and corn, we get this total for the first year, this is for the second, and so on, finishing with this last year. So again, based on these cash flows in the total, we can then find the present worth given the 20% rate, and so that evaluates to 19,926. So that's important, right, to realize that the inflation could be different for different commodities in different years, and it doesn't have to be, right, the same change. The years could be different. Here's another example of different inflation rates per period. In years 1 through 5, the inflation rate was 5%, and the real interest rate was 10%. So remember, the real interest is an inflation-free interest. It's I prime. So from F and the I prime, we can get the market rate if we needed to. So we use this equation to get the market rate. 1 plus I is 1 plus I prime, or this real rate, which is 10%, multiplied by 1 plus F, and then F is an inflation rate. This is 5%. So that's exactly what we have. And then this simplifies, right, when we discount, or when we get rid of the 1, this simplifies to the market rate being 15.5%. And so in year 6, 8, now things change. Inflation rate increased, but the real interest rate is still remain 10%. So again, solving this, we're gonna get 18.25% market rate. And then in the years 1 through 5, inflation rate was 5% and the real interest rate was 10%. So that actually, I apologize, not 5, should be 3% here. So if we had a smaller rate, if instead we had a smaller inflation rate, then we would get a smaller market rate too, right, even for the same real rate as before. So here's an example of inflation rate being 0. So then we have those before tax cash flows. We have the initial cost of 12,000, and that's towards the equipment. So this is an asset that could be depreciated, and we're depreciating it using straight line depreciation throughout the 6 years. So 12,000 divided by 6 is going to be 2,000. And then these are the before tax cash flows of $2,918. And so then we're gonna get the taxable income. The taxable income is simply gonna be, right, a percentage of the, or sorry, not percentage, but subtracting the depreciation from the income, right? So if we have this income, this is our income. We subtract 2,000 from it, we're gonna get the taxable income, and then to get the tax, right, we multiply it by the tax rate. So some incremental tax rate here gives us this much in terms of tax. So notice all of these are the same. The same straight line gives us the same depreciation amount. So when we subtract, we're gonna get the same taxable income each year. Subtracting from this income in each year, we subtract the straight line depreciation amount. We get the taxable income, and that's the same for all 6 years. And so the taxes also is gonna be all the same, given that we have the same incremental tax rate. So then from the tax and the before tax cash flow, we're going to subtract from the before tax cash flow, we're going to subtract tax, and that gives us the after tax cash flows. So this is just from 2,918. We subtract $422.28. We're going to get $2,495.72. And then we can find the rate for before tax cash flows. This is going to be the rate based on these cash flows here. Then for after tax cash flows, the rate is going to be, the internal rate of return is going to be 6.72%. So again, smaller. But then this is in terms of actual dollars. Then we can also take into account inflation. Because inflation is 0, when we discount this A, it just dividing it by 1 to whatever year, right? 1 to the 1, 1 to the 2, and so on. This is simply remains the same, right? So the actual is the same as real if inflation is negligent, right? If it's 0. And so that gives us the same rate of return. However, right, if the inflation rate increases to say 5%, now for the same exact amounts, right, as we said before, right, it would actually give us a higher income. Why? Because, right, it's going to be 5% more. So let's take a look, right? So here we have 2,918. So let me show this in how it changes. We're gonna basically multiply each of this by 5% to get these cash flows. So we're gonna do this in Excel. Alright, so I already entered this 2918 from the previous example. I want to find the actual inflated, right? So this income is going to be inflated because there's inflation of 5%. So the prices are going to be 5% higher. So you can see this is just going to be, right, this uninflated multiplied by 1 plus 5% inflation to however many periods we have here, right? So this 1 in this case for first year. And as you remember, this was always the same, right, for all the years. Now, when we just scroll this one through too, see how it changes? We just multiply this by the 1 plus the inflation rate 5 to the, however many years, in this case 2, and so on. So it increases. And so if you look at these and you compare them, this might be a little too small. Let me increase it just a little bit. So now if you compare these to these, they're identical. This is how those were computed. And let me just increase the decimal signs. Well, I'm doing all. So now you can compare these to these. They're exactly the same, right? And what it shows that this 2918 that we had in the previous example is no longer going to give us 2918 income. It's going to be 5% higher income because of the inflation. So now that we found that, the next thing is the straight line depreciation is just as before, right? This 12,000 is just split into 6 years equally using the straight line depreciation. Then we subtract those two, the before tax cash flows and straight line depreciation. They're subtracted to get the taxable income, and each year is the same thing. From here, we subtract this to get this. From here, subtract this to get this, and so on. And so then, from taxable income, we just multiply by the same incremental rate as we had in the previous example, and we get this amount of tax. So this tax is now subtracted from each of these, right, these before tax cash flows. and that gives us after-tax cash flows in terms of actual dollars. However, we have the inflation of 5, right, of 5%, so then all of these amounts here, there, to get the new amount, we're dividing this amount by 1 plus f to the 1. To get this amount right here, the after-tax real dollars in year 2, we divide the after-tax actual dollars in year 2 by 1 plus f to the 2 years, right, to the second year, and so on, right? And so then you see, for before tax cash flows, this was the rate, right? When we use all of these and we plug the rate in Excel, for example, it will give us the 17.59%. When we use all these values and plug in the rate function in Excel, we get 10.18%. So that's our incremental rate of return for actual after-tax cash flows. But for real after-tax cash flows, it's only 4.94%. So this is inflation-free increase, right? An inflation-free rate, internal rate of return. So now let's take a look at this, all right, in terms of using the spreadsheet. So general inflation rate is 3%, labor cost is going to increase at 6%, transportation cost is going to increase at 5%, and real interest rate is going to be 7%. So notice real interest is actually inflation free. This is the inflation rate. So this is I prime, this is the F. And then we also have the labor cost going to increase at different rate versus the transportation cost. So now we can get the market rate based on the inflation rate of 3 and the real rate or inflation free rate of 7. So from this equation that we had, we're going to get I of 10%, 10.21%. So then, using that in our calculations, we're going to have 4 years. These are labor costs in terms of actual dollars. This is the transportation in terms of real dollars. Again, we need to do oranges with oranges. So because labor cost and actual, we can then change our transportation cost in terms of actual as well. So translating into actual, we simply need to multiply these real into inflation to take into account inflation. So we're multiplying this 40,000 by 1 plus 3% to the first year. Then this one is 1 plus 3%. Actually, I apologize, not 3%, 5%, because the transportation cost is going to increase at 5%. So that's a general inflation rate. This is where we're going to translate the total amounts using the general rate. But transportation increase at 5%, so we're going to use the 5%. So here, I apologize, here we're using 40,000, we multiply it to 1 plus 0.05 to the first year. And then here we're going to multiply the 60,000 by 1 plus 5% to the 2 for the second year to get the second year actual cost, right? So we are just inflating the real cost. So this is how we get these values for transportation, and when we add those together, right, the 120,000 for labor of actual dollars and then actual cost for transportation of 42,000. So 120,000 plus 42,000 is going to be 162,000. And that's what we do for all the years, right? We just add the labor in terms of actual and transportation actual to get the total amount. But then this is our actual. We still want to know the real amount. So to find the real amounts, we here to discount the, this is the, it contains inflation. To find the real, which is inflation free, we're going to discount, right, or divide this by the general inflation rate. So it's going to be, we're not going to divide here, we were multiplying by 1 plus 5%. Here we're dividing by 1 plus 3%, right, because it's general rate. So 1 plus 3% we divide by 1 plus 3% to the first year, to the 1 for the first year, and then dividing by 1 plus 3% here to the second for the second year to get this. And then for the third year, we divide this, we take this amount, the actual amount in year 3, we divide it by 1 plus 3% general rate to the 3 for the third year to get the real dollars for the third year, total real dollars for the third year, or inflation-free dollars, and so on, right? Also for the fourth. So then we can also find the present worth based on that, and then the actual uniform cost. So you can see, right, in terms of present worth how things are, and in terms of the actual uniform cost. So the actual uniform cost in terms of real dollars are going to be smaller. So here's another example in terms of inflation effect on after-tax calculations. So we have a 0% inflation rate. And it's the same example as before. The only difference is before we had the straight line depreciation. Here we're going to use modified accelerated cost recovery system depreciation. So you can see here that the depreciation amount is no longer 2,000, right? When we use the straight line, we just divided this 12,000 by 6 and got 2,000, and it was 2,000 everywhere. Well, for a modified accelerated cost recovery system, it's different. So we're using the 5 year, this is a 5-year asset, and so we're using those, right, for 5-year assets. We first had, right, we're discounting the entire amount of 12,000, and then we multiply it by 20% here, and so on, right? So just from table, this is from table 11.3, from chapter 11 depreciation. And so we just multiply this 12,000 by 20% and so on, right? All those percentage rates that we get for the for each of the years from table 11.3 that is given in the column for a 5-year asset. So then it gives us different depreciation. So when we subtract the depreciation amount from before tax cash flows that are still the same, it's going to be a different taxable amount. So notice one of the taxable amounts is even negative, and that results in a negative tax. So then it gives us these after-tax cash flows, which is simply right from the before tax, we're subtracting the tax, and it gives us after-tax cash flows. So we got all of these, and then when we look at all of them together from 0 to year 6, we can find the rate of return for these cash flows. So notice from before tax cash flows, which the rate was 11.99, to the actual dollars after tax cash flows is going to be 7.29, and because the inflation rate is 0, then these values right here do not change, right? Because we would just divide it by 1 each time, and so they don't change. So the internal rate of return also doesn't change. So whatever we have in actual is the same in terms of real because the inflation is 0. However, if the inflation changed, right, again, the same thing, the only difference, right, as before, we have the modified accelerated cost recovery system, all the same values, the only difference is the inflation. So instead of 2,918, as we had for 0%, right, this was our income. Now the prices are going to increase at 5% rate, so we're getting these values. I have computed it already previously in the spreadsheet to show you how we did that. Right, so we got these inflated income values, inflated by 5%. The depreciation charges are still the same, so when we subtract those, we're going to get taxable income, and then multiplying by incremented rate, we get the tax, and then this tax is subtracted from before tax cash flows to get the after tax cash flows in actual dollars. And then the actual dollars need to be discounted by the inflation rate. So they're going to be, each of them, they're going to be divided by 1 plus f in whatever their year, right? So if you want to find the real rate in year 1, then the actual rate in year 1, and actual, cash flow in year 1 is going to be divided by 1 plus f to the 1 because year is 1. But if you want to find the actual tax cash flows for in terms of real for say year 3, then the after-tax cash flows in actual dollars for year 3 has to be divided by 1 plus 5% and taken into to the third degree. And so we get these real cash flows, we get the actual cash flows. For actual, this is the rate, and we have much smaller rate for the real cash flows when we discount 5% inflation rate. But notice, right, if we just simply subtracted 5% from this 10.96, then we wouldn't get the correct value. So it's important to take into account, right, that this is, you can't just simply subtract the inflation rate. Alright, I hope this was useful. Thank you. And this concludes my engineering economy lectures. Have a wonderful day.